Hey guys, this lesson is 9.3 from Calculus BC, and here we're going to be learning two more of our series test. We're going to be learning the integral test and then the P-series test, okay? So to begin with, for the integral test, the way you're going to spot that you might want to try this test is if you see a function that looks like it's going to have an easy antiderivative that you've learned in the past, okay? One of the most common ones that you'll spot is like a u sub scenario. So in order to use the integral test, you first have to confirm that the function that you would be replacing that's given in the series is positive, continuous, and decreasing, okay? And that we're testing numbers greater than or equal to 1, okay? So we're going to replace that a sub n in the series with the variable f as your function. Then we can say that if we're solving for this series from 1 to infinity, then we can test the integral from 1 to infinity of that function, right? And then if this integral converges to a number, we can state that this also converges to that number. And if this diverges, then we can state that this will also diverge, okay? So not too difficult. It is a little lengthier because you have to check these three. So let's start with this first one here. When I look at this function, the reason why I would want to try the integral test is because when I look at this fraction, I see that the denominator's exponent is 1 higher than the numerator, which is a key indicator for using u sub, okay? But before I can move there, I do have to check positive, continuous, and decreasing. So is this positive? Okay, well, I don't see any negative sign here. This is the easiest one to check, so it is positive. Easy enough? So let's check the next one. Is it continuous? Well, on a fraction, the way I check if something is continuous is by setting the denominator equal to 0. If I get a number in between my range here from 1 to infinity, then I would have a discontinuity at that spot. If I don't get a number between 1 and infinity, then I'm good and it's continuous. So n squared plus 1 equals 0. Move over that 1. When I do the square root of a negative number, I get an imaginary number. An imaginary number is not in between 1 and infinity. Therefore, it is continuous. Okay? Lastly, is it decreasing? Okay? Let's come down here for this. Now, just by looking at this, let's say I test the number 1. 1 over 1 squared plus 1. My denominator, as I start adding a bigger number, a bigger number, a bigger number, this squared plus 1 is going to keep making my denominator bigger and bigger and bigger than my numerator is, right? We talked in a previous video that if my denominator keeps getting bigger, my number keeps getting smaller, right? So that's one way of seeing that it decreases. But if you're in an FRQ and you need to show a little more work behind it, we've learned previously that I can test something is decreasing by checking that the first derivative is negative. So I'm going to do the first derivative. If this is my function f, then I'm going to say, let me scoot down a little bit. F prime is going to be, right, low d high minus high d low over low squared. All right, so I'm going to clean that up a little bit, and I'm going to have n squared plus 1 minus 2n squared. So n squared minus 2n squared is going to give me a negative n squared plus 1 over n squared plus 1 squared. So first derivative test says that I set both the numerator and the denominator equal to 0. Now I know that when I set this denominator equal to 0, I'm going to end up putting that inside equal to 0, which is technically what I just did here. And that gave me an imaginary number. So I can skip that step and just say, all right, negative n squared plus 1 equals 0. I'll have n squared equals 1, n equals plus or minus 1, right? So those are my, my possible max and mins, right? So if I'm analyzing this question only from 1 to infinity, I don't care about that negative 1, and I'm just going to test 1. Now I'm putting this so far left because I don't even care what happens to the left of 1. I only care that if from 1 to infinity, this function is decreasing. So from 1 to infinity, I'm going to test f prime of 2, something easy, right? So if I do f prime of 2, I plug that in the derivative here. I have negative 2 squared, which would be a negative 4 plus 1 over, no matter what I put in that denominator, it's going to be positive, right? So negative 4 plus 1 is going to be negative over positive, which gives me negative. I just confirmed that this indeed is decreasing, okay? So again, these questions are lengthy because you have to test those 3. Now that those 3 have come out, positive, continuous, and decreasing, now I can go ahead and do my work of testing my infinite integral from 1 to infinity of n over n squared plus 1. I learned in my previous BC chapter that I need to rewrite this as the limit as b approaches infinity of the integral of 1 to b of n over n squared plus 1. And I forgot my little notation here, dn, right? Because n is my variable. So now here I am hopefully catching again this u sub. So if u is going to be, n squared plus 1, then my u prime is going to be 2n, which means I'm missing a 2 here. So I want to put that 1/2 up front, and you can put it all the way up front. So now I have half times the limit as b approaches infinity of the integral from 1 to b. Here's my u prime over my u. I know the answer to this antiderivative is going to be an ln of absolute value of u. And this is going to go from 1 to b. I'm going to bring down this notation here, half times the limit as b approaches infinity. And I can say half times ln absolute value of, if b is infinity, I'm going to put infinity here, minus ln of 1. Now technically we don't need those absolute values because infinity and 1 are both positive, okay? And I know that ln, if I think of the graph, right, an ln graph goes like this, where this right here is 1, 0, and as I shoot to infinity, I can see this is going to go on to infinity. That might help you answer these if you don't have it memorized. So I have half times ln of infinity is infinity, minus ln of 1 we said was 0. Infinity minus 0 is infinity, and half times infinity is infinity. Therefore, this diverges. So they love putting these questions on an FRQ because there is so much to test here and so many places to give points. You can give points on your work on derivatives over here and concluding that it's decreasing. You can give points to setting up the series as an integral. Now we're testing you in series. And then you can also give points to your infinite integrals and your notation. And then you can give points to concluding that it diverges. So much to test you on in one question. It's a great FRQ question. Let's look at this next question. The infinite series of 1 over n squared plus 1. Now, if you see this question randomly on an AP test or on a chapter test, hopefully your eye is drawn to the fact that this looks like an arctan question. And I'm going to tell you now, if you're taking BC, have that memorized. They love throwing an arctan in the AP test. Happens all the time. Okay, so again, if I want to use the integral test, I first have to check, is it positive? Now, hopefully you see, no negative sign up there, so you are good. Is it continuous? hopefully you start getting good at that. If you see an n squared plus 1, anytime this is a squared and a plus, this is always going to be positive. I can never get a negative there. But if we are doing an FRQ, we want to show our work of setting that denominator equal to 0. Right? I get that imaginary number. Obviously, an imaginary number is not in between 1 and infinity, so I am continuous. Next, I'm checking decreasing. Right? Hopefully, you can start catching that denominator is going to keep getting bigger, meaning the number is going to keep getting smaller. A nice quick shortcut on a multiple choice. But if you need to show your work, you're going to do that first derivative. So I have low d high minus high d low over low squared. All right, this cancels. I'm left with negative 2n over n squared plus 1 squared. That denominator is going to work out just like this up here. So I'm going to be able to skip that step. I don't have to do it. Now, I'm going to set my numerator equal to 0. And I get 0, which means if I only care about numbers from 1 to infinity, I'm going to put my 0 over here because I don't have to check that left side. But I'm going to check a number to the right of it. So f prime of 2, if I plug that into my derivative, I know that my denominator, because it's squared, will always be positive. And then 2 times a negative 2 is going to give me a negative 4. So negative over positive is negative. That means this is, in fact, decreasing. Okay? Now that I've proven continuous, positive, and decreasing, I can move on to the integral from 1 to infinity. And I pick 1 to infinity because of these here. Of 1 over n squared plus 1. Just like my previous question and my previous BC chapters, I need to set this up properly and say the limit as b approaches infinity of the integral of 1 to b of 1 over n squared plus 1. And once again, I forgot my dn. I'm sorry about that. So now, again, hopefully your eye catches that this is an arctan. Memorize it. Know it, okay? So I can say the limit as b approaches infinity of arctan of n, right? Because my variable is still n there, from 1 to b. Now I can say arctan of b, which b is infinity, minus arctan of 1. Now please know that on an AP and an FRQ, you can usually stop at this step, but if you have trig functions, you have to continue, okay? So let's analyze the graph of an arctan, okay? I think this is really going to help. Now, if you don't remember your trig graphs, please watch my video. It is so helpful, and knowing this graph is going to be so useful, okay? So that is my tangent graph. So if I say arctan, it just means that I'm asking, like Jeopardy style, you know, I'm giving you the y and I want the x. It's inversely being asked, okay? So the question is, what am I plugging in if tangent is approaching infinity? Well, positive infinity means tangent is going up. Negative infinity means tangent is going down. So as tangent approaches infinity, is always going up, what x value am I getting closer to? And hopefully you can spot it right here that it is pi over 2. Okay? Now with the graph, you also know that your amplitudes is at 1 and negative 1. And you know that this spot halfway is where I hit the amplitude, and that is pi over 4, which gives me my next answer. But you can also recognize from the unit circle, right, that at this spot right here, where I have radical 2 over 2, comma radical 2 over 2, is where my tangent equals 1, and this is at pi over 4. So different ways to recognize this. Now on an FRQ, you would be able to stop. But if it's a multiple choice, you have to keep going. Get a common denominator. And I am working with 2 pi over 4 minus pi over 4, which gives me pi over 4, and therefore it converges. Okay. Our next test is called P-series. This is a very common and very easy, quick series to solve. Let me just warn you, it is a look-alike of the geometric. They look very similar. There's just one small difference, okay? A P-series is the infinite sum of 1 over n raised to p, where n is your variable and p is a number. Geometric has the number being raised to the variable. Here we have the variable being raised to the number, okay? So the P-series states that if p, that number in the exponent, is greater than 1, it converges. If it is less than or equal to 1, it diverges, okay? A very popular specific type of P-series is called the harmonic series. This is one that always diverges. It's a good one to memorize. And that is when p equals 1. So it's just 1 over n, okay? And if you test out adding these numbers in a calculator, you're going to see by doing partial sum that it keeps getting bigger and bigger, okay? So a good one to memorize, but let's check out some more complicated P-series, okay? So does this series converge or diverge? Remember, if I don't have a 1 in this numerator like it's expected, I am allowed to move that to the front like a coefficient. So I can say 3 times the infinite series of 1 over n raised to 5 over 3. Now I can call this a P-series, right? My P is 5 over 3, which is a number that is greater than 1. Therefore, right, those 3 dots means therefore, it converges. Easy enough? Let's take a look at the next one. Here, instead of them writing out the series in series notation, they wrote it out more as an infinite sum. So I can do the work really quick and come up with that function, okay? Just by analyzing, remember, let's not look at this one for the moment. All of my numerators are 1. And if I look at my denominators, I notice that they all have a cube root. The inside of the cube roots are different numbers, 4, 9, 16, 25, okay? If I try to analyze the pattern there, if this is my second term, this is my third term, this is my fourth, and this is my fifth, what relationship do those numbers have? Well, I know that 2 squared is 4, 3 squared is 9, 4 squared is 16, and 5 squared is 25. So I can say that this is the infinite sum of 1 over the cube root of n, right? Because 2 is n, 3 is n, and so on, squared. We see that? And that goes back to making sense that this is 1 because 1 raised to anything is 1, and the root of 1 will always be 1, and 1 over 1 is 1, okay? Now, if I want this to look like a P-series, I want to write this radical as a fractional exponent. So I can say that this is the infinite series of 1 over n raised to 2 over 3. Therefore, my P is 2 over 3. And since 2 over 3 is less than 1, then this diverges. Put my little therefore sign, diverges. All right. And let's move on to our last question. So similar to the first, I don't have a 1 in this numerator. So I can move this to the front and say 3 times the infinite series of 1 over n raised to pi. So in this case, my P is pi. All right. Pi is 3.14. It is a number that is bigger than 1. Therefore, this series converges. And you're done.